Welcome to our course on heat transfer. This video was made with the support of Energy. The introduction to heat transfer is divided in several lessons. There is at least one video devoted of each of these lessons. Let's start with the first one, concepts and definitions. It aims to provide you a set of definitions that will help you understanding better the next videos. Let's start with the definition of heat transfer. But before giving you a scientific definition, let's start analyzing the relevance of temperature and use of energy in your daily life. At home, you are used to talk about high and low temperatures. How hot or how cold is something? You know that space heating or air conditioning is needed for keeping a comfortable temperature. A fan can help you to withstand with high temperatures. And a heater can help you to provide comfortable temperatures in winter. In addition, you may know that heating water is needed to have a pleasant shower. Making your life more comfortable needs expending energy. Reducing the energy bill can be done by increasing the energy efficiency.
Thermodynamics and heat transfer can help you, for instance, to save money in your energy bill by improving the energy efficiency of your house. In the same way, for saving energy in industry.
Let's talk now about thermal energy. As you may know, there are many forms of energy: mechanical, electrical, chemical, nuclear, and thermal. Thermal energy is created from the vibration, translation, and rotation of atoms and molecules within substances. The faster they move, the more energy they possess, and the hotter they become. Thermal energy sometimes is also called heat energy or only heat, and it is quantified in joules. For example, a traditional filament light bulb transforms electrical energy into light and thermal energy. Electrons in it gain kinetic energy and, therefore, the temperature of the filament increases. As consequence, heat is released to the ambient. The filament also emits light when it reaches a sufficiently high temperature. However, in thermodynamics, heat is energy transferred to or from a thermodynamic system by mechanisms other than thermodynamic work or transfer of matter. Therefore, heat refers to a quantity transferred between systems, not to a property of any one system or contained within it. For a closed system, the variation of its internal energy, delta U, depends on the thermodynamic work done by the system on its surroundings, and the energy gained or lost in the form of heat.
The conservation equation can be written as Q minus W equal to delta U. This is something you probably know from a previous course in thermodynamics. Internal energy is a principal property of the thermodynamic state, while heat and work are modes of energy transfer by which a process may change this state. For the transfer of energy in the form of heat, the driving force is temperature. Whenever there exists a temperature difference between media, or a temperature difference in a medium, heat transfer must occur. Therefore, heat transfer can be defined as the transfer of thermal energy due to a spatial difference in temperature.
Let's go beyond thermodynamics. Thermodynamics is a branch of physics that deals with heat, work, and temperature, and their relation to energy, entropy, the physical properties of matter, and radiation.
The thermodynamics Zeroth law provides an empirical definition of temperature. Thermodynamics also explains that, by putting two systems in contact, their temperature will evolve until reaching equilibrium. The term thermodynamic equilibrium indicates a state of balance in which all macroscopic flows are zero. In an equilibrium state, there are no driving forces between macroscopically distinct parts of the system. In this example, both systems have the same temperature when the equilibrium is reached. We will call it TEQ. Open questions. What is the equilibrium temperature? How much energy is transferred? Stop his video here and try to answer these questions. Did you answer these questions by yourself? They can be answered by applying the first law of thermodynamics, also called energy conservation principle. It postulates that, with the system isolated from the outer environment, the initial energy is conserved throughout the thermal evolution of both bodies. In this example, this means that energy gained by solid 2 plus the energy lost by solid 1 equals 0. One of them will be positive and the other negative. This will allow you to calculate the equilibrium temperature and the amount of energy transferred, or heat. A practical consequence of the second law is that thermal energy does not spontaneously flow from a colder body to a hotter body. In heat transfer, this means that energy always flows from the point or system at higher temperature to the point or system at lower temperature. Keep all this in mind when solving heat transfer problems. Let's make new open questions. How the process of reaching thermal equilibrium takes place? At what velocity does it take place? These questions are not answered by thermodynamics. The discipline of heat transfer seeks to quantify the rate at which heat transfer occurs in terms of the degree of thermal non-equilibrium. This is done through the rate equations. In heat transfer, then, we introduce the time variable and we will work with the concept of thermal power or heat transfer rate. It is defined as the amount of energy transferred in the form of heat per unit time. Rate equations are relationships between the heat transfer rate, Q, and the driving force, which is the difference of temperatures delta T.
Transient state and steady state. For the set of two systems at different temperature put in contact, the transient regime is the interval where temperatures change over time. There is also heat transfer when the temperatures of the bodies remain constant over time, namely, the steady state. As you can see, it is needed to have a heat source and a heat sink to keep temperatures constant during the steady state. Don't miss the next video about the equation of energy conservation.